Hello everyone, welcome to my channel on engineering mathematics. In this video, we are going to see examples based on direct formulas and linearity property of Laplace transform to find inverse Laplace transform of the given function. In my previous video, I have already discussed how to find inverse Laplace transform of the given function. To refer that video, please find the link in the description box. So let us proceed with first example of this video. Here I asked to find L inverse of 3 upon s square plus 3 square. To find L inverse of 3 upon s square plus 3 square, I will suggest you to think whose Laplace transform is this function 3 upon s square plus 3 square. If you don't remember, recall Laplace of sin at, which is a upon s square plus a square. Clearly, L inverse of a upon s square plus a square is sin at. Now you see that this function is exactly similar to this function if a is equal to 3. Therefore, L inverse of this function is sin 3t. Now let me increase the difficulty level in example number 2 by removing this 3 from the numerator of this function. Here in this example, I ask you to find L inverse of 1 upon s square plus 3 square. Now it is clearly seen that since this 3 is not there in the numerator, L inverse of this function cannot be directly written as sin 3t. For that, we have to first bring 3 over here in the numerator. To do so, I will multiply and divide this function by 3. So L inverse of 1 upon s square plus 3 square can be seen as 1 by 3 into L inverse of 3 upon s square plus 3 square, which is equal to 1 by 3 into sin 3t. I hope you guys understood this answer. Now let us proceed for next example. In this example, we have to find L inverse of s upon s square plus 3 square. To find L inverse of s upon s square plus 3 square, think whose Laplace transform is this function. If you don't remember, recall Laplace transform of cos at. It is s upon s square plus a square. So L inverse of s upon s square plus a square is cos at. It is clearly seen that this function is exactly similar to this function if a is equal to 3. Therefore, L inverse of s upon s square plus 3 square is cos 3t. Now try to solve this fourth example. Here we have to find L inverse of 1 upon s square plus 4 square. If you compare this function with this one, you will see that s is missing over here. If there was s, we would have written L inverse of s upon s square plus 4 square as cos 4t. But since s is not there, what you will do? Can you bring s over here by simply multiplying and dividing by s? The answer is no. Because if you do so, you cannot take out 1 by s and simply find out L inverse of s upon s square plus 4 square, the way we did in the previous second example. So what you can do? You can use that technique only with the constants. Because L inverse is linear operator and constant can be taken out while operating this L inverse on the function. So to find out L inverse of 1 upon s square plus 4 square, you have to multiply and divide this function by 4. So L inverse of 1 upon s square plus 4 square can be seen as 1 by 4 into L inverse of 1 upon s square plus 4 square, which is sin 4t. Therefore, final answer is 1 by 4 sin 4t. I hope you guys understood this answer. Now let us proceed for next example. Here we have to find L inverse of s plus 2 upon s square plus 3 square. To find this L inverse, we first distribute this function over this addition. We write it as s upon s square plus 3 square plus 2 upon s square plus 3 square. Now you can use linearity property of L inverse and distribute this operator over this addition in this way. Now we have to find out L inverse of S upon S square plus 3 square. First think, whose Laplace transform is S upon S square plus 3 square? If you don't remember, recall Laplace transform of cos AT. It is S upon S square plus A square. Therefore, L inverse of S upon S square plus A square is cos AT. So clearly, L inverse of S upon S square plus 3 square is cos 3t. Now to find L inverse of 2 upon S square plus 3 square, we have to take out this constant. Then we will be left with 1 upon S square plus 3 square. 1 upon S square plus 3 square is nobody's Laplace transform unless and until you have 3 in the numerator. So we will bring 3 in the numerator by multiplying and dividing this function by 3. That 1 by 3 is a constant one you can take out. So outside we will have 2 by 3 and inside you will have L inverse of 3 upon S square plus 3 square, which is nothing but sine 3t. So L inverse of 2 upon S square plus 3 square is 2 by 3 sine 3t. Now let us go for similar such example. Here we have to find L inverse of S plus 3 upon S square plus 4 square. Just like this example, you can first distribute this function over the addition in the numerator. Then using linearity property of L inverse, you can find out L inverse of S upon S square plus 4 square and L inverse of 3 upon S square plus 4 square. L inverse of S upon S square plus 4 square is cos 4t and L inverse of 3 upon S square plus 4 square can be found by multiplying and dividing this function by 4. So outside you will have 3 by 4 and inside you will have L inverse of 4 upon S square plus 4 square, which is sine 4t. I hope guys you understood this answer as well. Now let us proceed for next example. Here we have to find L inverse of 1 upon S minus 3. Do you remember any function whose Laplace transform is 1 upon S minus A? If you don't remember, find Laplace of e raised to at. You will see it is equal to 1 upon S minus A. So this function is similar to this one when A is equal to 3. So clearly L inverse of 1 upon S minus A is e raised to at. Therefore L inverse of 1 upon S minus 3 is e raised to 3t. Now on similar lines we will solve example number 8. Here we are asked to find L inverse of 3 upon S plus 4. To find its L inverse, we first take out that 3 as it is constant. Then we will be left with L inverse of 1 upon S plus 4. Now think, whose Laplace transform is 1 upon S plus 4? If you don't remember, recall Laplace of e raised to minus at. It is 1 upon S plus A. So here A is 4. Clearly L inverse of 1 upon S plus A is e raised to minus at. Therefore L inverse of 1 upon S plus 4 is e raised to minus 40. Yes, you are correct. Now let us proceed for ninth example. Here we have to find L inverse of 2 upon S square. To find this L inverse, I would like to recall Laplace of t raised to n. Laplace of t raised to n is n factorial upon s raised to n plus 1. Therefore, Laplace inverse of n factorial upon s raised to n plus 1 is t raised to n. Now, if I put n is equal to 1 in this, I will have Laplace of t is equal to 1 factorial upon s square. Therefore, L inverse of 1 upon s square is t. Now, from this function, I will take out this 2, which is constant. We will be left with L inverse of 1 upon s square. And just now we saw L inverse of 1 upon s square is t. So I will simply write t over here. So 2t is L inverse of 2 upon s square. I hope you guys understood this one. Let us look at the example number 10. Here we are asked to find L inverse of 1 upon S cube. Note that this S raised to n plus 1 term is over here, which is denominator of Laplace of t raised to n. So here 1 is added in the power of t. So what is power of t in this particular case? It has to be 2. So n is 2 in this particular case. We should have 2 factorial in the numerator of s raised to n plus 1 or s raised to 3. But we don't have 2 over here. So we have to bring it over here by multiplying and dividing by 2 to this function. So we will write 2 outside this L inverse and inside we will have 2 upon s cube. So L inverse of 2 by s cube will be equal to t square. So I will write this as 1 by 2 L inverse of 2 upon s cube, which is nothing but t square. Guys, please write me in comment box whether you are understanding these solutions or not. Now let us go for 11th example. Here we have to find L inverse of 3 upon s square minus 3 square. Ask yourself whose Laplace transform is of the kind a upon s square minus a square. If you don't remember, recall Laplace of sin h at. It is a upon s square minus a square. So these two functions are exactly similar at a is equal to 3. Therefore, I can write L inverse of 3 upon s square minus 3 square as sin h 3t. Similarly, we will find out Laplace inverse of 2s upon s square minus 4 square. First, we will take out this 2 constant and we will write this as 2 times L inverse of s upon s square minus 4 square. Ask yourself whose Laplace transform is s upon s square minus 4 square. If you don't remember, recall Laplace of cos h at, which is s upon s square minus a square. So here a is equal to 4. Therefore, L inverse of s upon s square minus 4 square is cos h 4t. So 2 cos h 4t is L inverse of 2s upon s square minus 4 square. Now, in next example, I am going to combine all the functions whose L inverse we have seen so far. So this is going to be an interesting one. Look at example number 13. Here we are asked to find L inverse of sum or difference of these 4 terms or 4 functions. To find out L inverse of this huge function, we will use linearity property of L inverse. We will distribute this L inverse over these additions and subtractions in this way. So this can be written as L inverse of first function plus L inverse of second function minus L inverse of third function and so on. In the numerator of first function, there are 2 terms separated by plus sign. Once again, you can distribute this L inverse over this addition. So I can write this as L inverse of 1 upon s cube and second term will be then 2 times L inverse of 1 upon s square. Remaining terms as it is. Now let us write inverse Laplaces of all these functions. In my previous examples, we have already seen what is L inverse of 1 upon s cube, 1 upon s square and so on. If you don't remember their formulas, you can refer the recall section over here. So L inverse of 1 upon s cube is nothing but 1 by t square. L inverse of 1 upon s square is t. L inverse of 1 upon s minus 3 is e raised to 3t. And L inverse of s upon s square plus 2 square is cos 2t. Also, L inverse of 2 upon s square minus 2 square is sin h 2t. So this is inverse Laplace transform of the given function. I hope guys you understood this solution. If you are not getting any step, please pause the video and check the calculation. Now it is your turn to solve some examples. You can consider these 2 examples as practice examples. Their final solutions are also given below. Guys, please write in comment box whether you got these answers or not. If you like this video, please click the like button and share this video among your friends. I will be coming with more such interesting videos. Till then, keep watching. Thank you all of you. Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.